we start the final lecture in this course, Lecture 10-3, Active Filters. Students should be reading Chapter 8 of the course notes in order to get supplemental instruction on this topic. At the conclusion of this lecture, students should be able to define an active filter and describe two advantages of active filters. Identify the characteristics of an active filter, including the gain, bandwidth, center frequency, cutoff frequency, and quality factor, and compare and contrast active and passive filters. Active filters can be described the same way we describe passive filters, except they include more than just resistors, inductors, and capacitors. Active filters also include an operational amplifier. The advantages to using operational amplifiers are that they may be less expensive than inductors, and the maximum magnitude can now exceed 1. Additionally, the addition of a resistive load will not alter the passband magnitude or the cutoff frequency of an active filter because since they have op amps, they have a very high input impedance. However, the disadvantage in using an active filter is that it will require additional power for the operational amplifier. The first two types of active filters are the low pass and the high pass filter, and here we have given two example circuits that are in the frequency domain inverting amplifiers, but because there's a feedback capacitor on the left circuit, it becomes a low pass filter, and because there is an input capacitor on the right circuit, it becomes a high pass filter. So the transfer function is negative k omega c over s plus omega c, where k is equal to R2 over R1, and the cutoff frequency is 1 over R2c. Note that in the time domain, the low-pass filter behaves as an integrating amplifier. The right circuit is a high-pass filter with the transfer function negative k s over s plus omega c. The gain k is R2 over R1, and the cutoff frequency is 1 over R1c. And note that in the time domain, this circuit acts as a differentiating amplifier. For the system described by the following circuit, use analytical and qualitative techniques to determine the type of filter and characteristics such as transfer function, gain, bandwidth, and cutoff frequency. So the first thing we could do is redraw this circuit in the frequency domain. So we have the input Vi of S, the capacitor, which is 5,000, the inductor S times 0.5, and the positive terminal is tied to ground, and the feedback resistor is 15,000, and the output V naught of S. So first we will determine the transfer function. The transfer function is negative 15K over 5K plus S 0.5, which simplifies to negative 30K over S plus 10K. And what you notice here is that as omega goes to 0, the magnitude of h of j omega is equal to 3. And as omega goes to infinity, the magnitude of h of j omega is equal to 0. So we see here that we have a low-pass filter. And it's a low-pass filter with a gain of 3. So comparing this to our standard form, h of s is equal to k omega c over s plus omega c, and we have negative 30k over s plus 10k. And remember, k is a negative 3. Here we use the magnitude, which is why it was a positive 3. So we would have negative 3 times 10k over s plus 10k. So we get that the cutoff frequency is 10 kiloradians per second. So if we mark 10K on our graph here, and here's omega radians per second, we know that the point where we get 10 kiloradians per second, the magnitude is 3 over the square root of 2. So the pass band is 10 kiloradians per second, and the gain is negative 3, or if we're looking at magnitude, it's 3. It is possible to create a broadband bandpass filter where the second cutoff frequency is greater than 2 times the first cutoff frequency by cascading a low-pass filter and a high-pass filter and an inverting amplifier. Notice that the shape of this bandpass filter has, once again, the magnitude of the maximum value of K. The cutoffs are at 0.707 K, and beta represents the bandwidth, which is omega 2 minus omega 1. So if we look at our circuit here, the first circuit is a low-pass filter with a unity gain and a cutoff at omega C2, and it has a transfer function omega C2 over S plus omega C2. The second filter here is the high pass filter with unity gain and omega C1, so the transfer function is S over S plus omega C1. And the inverting amplifier has a gain of K, where K is equal to negative RF over RI. So now when we cascade these together, we get that the overall transfer function for this broadband bandpass filter is the transfer function of the low pass, the high pass, and the inverting multiplied together. So you get negative K omega C2S over S squared plus omega C1 plus omega C2S plus omega C1 times omega C2. So this is an approximation of a broadband bandpass filter. So for this one, the bandwidth actually ends up being omega C1 plus omega C2, but it's still approximately omega C2 because it's a broadband and this is so much bigger than omega C1. And the resonant frequency is still the square root of omega C1 times omega C2. An alternate simplified form of a bandpass filter is a passive high-pass filter cascaded with an active low-pass filter. And for this circuit, you would get that K is equal to R2 over R1, and omega C1 is equal to 1 over R1C1, which is the cutoff for the high-pass filter, and omega C2 is equal to 1 over R2C2, which is the cutoff for the low-pass filter. The disadvantage for using this type of circuit is that there is now no way to independently adjust for the gains and the cutoffs because they're all interconnected. However, the advantage of using this type of filter is it is fewer operational amplifiers than the circuit we just evaluated. It is also possible to create a broadband band reject filter where omega C2 is greater than or equal to 2 omega C1 by putting a low pass and a high pass filter in parallel and putting them in series with an inverting amplifier. So here's the block diagram for this circuit. You have an input which is a low pass filter with a unity gain at omega C1 and a high pass filter with a unity gain and omega C2. And then you have the inverting amplifier with a gain of K is equal to RF over RI. So here at the top we have the low pass filter. At the bottom we have the high pass filter. So you simply add those together with this summing amplifier, and you use the summing amplifier or inverting amplifier to produce the gain that you want, K. So when you write the equation for this, you get that K is equal to S squared plus 2 omega C1S plus omega C1 times omega C2 over S plus omega C1 times S plus omega C2. So once again, you would get that the resonant frequency, omega naught, is equal to the square root of omega C1 times omega C2, and the bandwidth beta is equal to omega C1 plus omega C2. In class activity 2, design a bandpass filter to have a gain of 20 decibels, a resonant frequency of 10 kiloradians per second, and a Q equal to 0.5. So the first thing we could make is we could make a sketch of what this bandpass filter should look like. So here we have the bandpass filter, and if it has a gain of 20 decibels, that means that K is equal to 10 to the 20 over 20, which equals 10. So the maximum value is 10. And the resonant frequency is 10K, where omega is radians per second. And one thing we could find are the cutoff frequencies, omega C1 and omega C2. So K is equal to 10, omega naught is equal to 10 kiloradians per second, and Q is equal to 0.5, which equals omega naught over the bandwidth. So the bandwidth is equal to 20 kiloradians per second. So omega C2 minus omega C1 is equal to 20 kiloradians per second, and omega C2 times omega C1 is equal to 10K squared. So solving these two equations, we get that omega C2 is equal to 24 kiloradians per second, and omega C1 is equal to 4 kiloradians per second, and omega C2 is going to be the cutoff frequency for the low pass filter, and omega C1 is going to be the cutoff frequency for the high pass filter. Since we know we want the gain to be 10, we want K, which equals R2 over R1, to be equal to 10, or R2 equals 10 times R1. So if we let R1 equal 2 kiloohms, R2 will equal 20 kiloohms. And the cutoff frequency for the low pass filter is going to be 1 over R2 times C2, and that has to equal 24K. So since we know we want R2 to be equal to 20 kiloohms, we're going to get that C2 is equal to 2 nanofarads. For the high pass filter, we have 1 over R1 times C1 equals 4 kiloradians per second. And since we know that R1 is 2 kiloohms, we're going to get that C1 equals 120 nanofarads. And now we can draw the circuit. We have an input, VI of S. Here we have the 2 kiloohm resistor and the 120 nanofarad capacitor for the passive high pass filter. And here's the ground. And now our feedback is the active low pass filter. Here's the feedback resistor and the feedback capacitor. The value of that resistor is 20 kiloohms, and the value of the capacitor is 2 nanofarads. And here's the output, VO of S. The transfer function, H of S, is equal to negative K omega C2S over S plus omega C1 times S plus omega C2, or negative 10 times 24K times S over S plus 24K times S plus 4K. Design a band reject filter to have a gain of 10 decibels and cutoff frequencies at 4 radians per second and 16 radians per second. So once again, the first thing we want to do is to find the gain for the filter. So we have 20 log base 10 of K is equal to 10, or K is equal to 10 raised to the 1/2. So K is equal to 3.16. For the low pass filter, we have that omega C1 is equal to 1 over R1 C1, and that has to equal 4. For the high pass filter, we have that omega C2 is equal to 1 over R2 C2, and that has to equal 16. So assume that we want all of our capacitors to be 10 microfarads. So if we use 10 microfarads, we'll find that R1 must be equal to 25 kiloohms, and R2 is equal to 6.25 kiloohms. Notice that we always select resistors in the kiloohm range to make sure that we don't draw too much current for the op amp. And you also don't want the resistors to be too large because that may cause noise issues with the op amp. Since we want the gain for our output op amp to be equal to 3.16, K equal to RF over RI is equal to 3.16. So we let R1 equal 1 kiloohm and RF equal 3.16 kiloohms. Since this is not a traditional resistor value, you could replace RF with a variable resistor or a potentiometer. Now we are ready to draw the circuit. So here we have the input, VI of S, and remember we're going to sum an active low pass and an active high pass filter. So here on the top I'm drawing the active low pass filter, where both of those resistors are going to be 25 kiloohms, and the capacitor is going to be 10 microfarads. Here at the bottom, I'm going to draw the high pass filter. The positive terminal is tied to ground, and we have a feedback resistor. Once again, the capacitor is 10 microfarads, and both of the resistors are 6.25 kiloohms. And now this is the input to my summing amplifier, which takes care of my gain. So the two input resistors, which are Ri, are going to be 1 kiloohm, and the feedback resistor is going to be 3.16 kiloohms. And that goes into the negative terminal on the op amp. The positive terminal is tied to ground, and that's V0 of S. The transfer function is h of s is equal to k times s squared plus 2 times omega c1s plus omega c1 times omega c2 divided by s plus omega c1 times s plus omega c2. So h of s is equal to 3.16 times s squared plus 8s plus 64 divided by s plus 4 times s plus 16. And this concludes today's lecture on active filters.